Climate model outputs often contain systematic biases because their spatial resolution and physical parameterizations cannot perfectly reproduce local climate conditions. Bias correction estimates these differences during a historical period and then applies the resulting correction relationship to a future climate projection. However, bias correction does not make a climate model perfect or eliminate uncertainty. It only makes the model output more consistent with local observations. In this example, daily precipitation observations from 2 stations have been loaded for 1993 through 2012. The climate model is CMIP6, the variable is precipitation, and the future experiment is SSP245. The methods were already tested in the Evaluation tab. We can now apply a selected method to the future projection. The station period is the calibration record from the observations. Here, the complete period from 1993 through 2012 is selected. The historical period comes from the historical GCM simulation. It must cover the same years as the observed calibration period. The downscale period defines the part of the future scenario that will be corrected. Here, we use 2020 through 2035. The observed and historical records should represent the same variable, dates, temporal resolution, and units. Otherwise, the estimated bias may be misleading. A sufficiently long calibration period is also important. Short records may not represent natural climate variability, seasonal behavior, or rare precipitation extremes. SD-GCM provides 6 methods. The final choice should be supported by the evaluation results, not simply selected because it is the default option. For this demonstration, we use the multiplicative delta method with monthly stratification. The resulting method is identified as delta M. A separate correction factor is calculated for every calendar month by comparing observed and historical GCM precipitation. The blue line is observed precipitation. Orange is the raw future GCM, and green is the bias-corrected future projection. The annual cycle compares the 12 monthly climatological means and reveals how the correction changes the seasonal precipitation pattern. The CDF shows changes across the complete distribution, including low values, median conditions, and the upper tail. Here, the corrected mean is 27.1, compared with an observed mean of 15.4. The corrected maximum also reaches about 461, while the observed maximum is approximately 149. Such a large correction is not automatically evidence of improvement. It is a warning that the result requires careful physical interpretation. Raw, monthly, and annual scales can be used to examine individual extremes, seasonal behavior, and interannual variability. Export for LLM generates a structured report containing the setup, method, statistics, change signal, annual cycle, and distributional information. It also provides a scientific prompt for diagnosing bias, evaluating seasonal changes, checking extremes, and assessing the selected method. It also provides a scientific prompt for diagnosing bias, evaluating seasonal changes, checking extremes, and assessing the selected method. Always compare several GCMs and scenarios, examine the extremes, and confirm that the corrected projection is physically plausible before using it in an impact study. Thanks.